here in the ocean section, and Kate Hedstrom from the University of Alaska. And they are going to be talking about principles of regional ocean modeling.
Okay, is it working? So thanks, Dan. Yeah, so as Dan indicated, I'm in the ocean section at NCAR. And I mean, I've been working with like global high-resolution Earth system model for quite some time now. But I did work with regional model like before coming to NCAR with Kate and Enrique, who's a postdoc there with Enrique. And so that's why I think Dan asked me if I could help with that presentation. But so hopefully I'm not too rusty because that was kind of like 10, 15 years ago, and I'm not going to ramble too much, but the good thing that if I say anything wrong, like Kate can correct me during the second part of the presentation. So I actually did steal that picture from Enrique. That's like two regional models on each the east and west coast of the US, overlay on top of Blue Marble. But I didn't feel too bad about it because I think I actually created that figure when I was a postdoc with him. So just like, yeah, the quick overview. We are just trying to give you some like kind of regional model 101 thing. And then like Kate will go a little bit more in depth with like map projection and the typical workflow to create a regional configuration. And she will finish with some actual example in trying to use them to illustrate some of the principles that we are going to highlight. So I guess if you're here, you're probably not a very hard audience to convince that regional models are actually very powerful and very useful tool. I mean, one thing we always highlight is that they allow for like higher resolution than global high resolution model, but they also like allow you to have much more like detailed coastal processes, which is critical for many applications, like including environmental management cases. So that's like fishery application, for example, or providing information to marine protected area. And those applications usually require to have like a regional focus and scale. We are at NCAR, so one obvious application also for us is to downscale like global climate model and assess like regional impact of climate change. One thing that is nice with regional model, they usually tend to be easier to tune by like global model. And what do I mean by that is a lot of time when you have a global model, you have like a great idea to make it better and you implement it and it make the model better in some location, but then degrade the solution somewhere else. That's usually something that you can go around with like a regional model because you are focusing the model on one given location in the first place. I guess the downside of regional model is like OBCs, so open boundary condition. And those are like not an easy question, and I will go into some detail about that later. So when you start to consider like a regional model, I think the first question is to ask what do I want to learn from that configuration? And sometimes the configuration sometimes can be like driven by a scientific hypothesis that you are interested to go after. Sometimes it can be driven by a specific funding opportunity. I think Kate will have some example of that later. And so essentially the main question is what the process is, what are the features that my model need to be able to resolve. And so yeah, answering this question is really like on the early stage, like going to help with the design later. So then like you move into regional knowledge. So it's important that you find out essentially everything you can on like that regional configuration. So what is the bathymetry look like? Do I have like deep canyon that are important for like cross-shelf exchange? Is there like seamounts that are known to have like strong impact on the regional oceanography? What are the major river? What are the major current in the region? In one of the aspects that is like the tide also. Do I need to have tide in my model? Tide sometimes are really important driver of like, for example, cross-shelf exchange. Rectified tidal flow has been shown to be non-trivial. And like, I remember like when I was starting to work with Enrique, like we had this configuration Northeast Pacific model where like if you don't have tide, essentially the circulation was, I forgot the detail now, but it was like, you had an island on the Bering Sea shelf and you have like a clockwise circulation if you don't have tide. And we know that the observed like in the real world, the circulation is going the other way. And when we turn on tide in that model, then we got the right answer. So the rectified flow was clearly, tidal flow was non-linear and important to have in the model. So then you go into like the regional domain. So now you start to have like a better idea of like what my model needs to resolve, what I need to include. And so you start to think more about like, okay, what my model is really going to look like, how big is my domain? So there is a few like rule here. You need to put the open boundary like away from big transition, both like in current and topography. You also want to have the boundary usually as far as possible because the boundary fundamentally are not really working well. So you want to put them away so they don't like pollute essentially your region of focus interests. And so another rule is like usually we try to, or we want to have the boundary normal to Hyderabad or like the main current. And this is because it's really help. As I say, the open boundary is usually, we can consider that they are not really working. So having the boundary normal will really help with having like less reflection inside their domain and like a cleaner boundary condition. One other thing is like we usually try to avoid to have like too big of a jump in resolution between the model that you use to provide your open boundary condition and your regional domain. So typically we think like 3 to 4 is often considered like a good ratio, but it's not always possible. And we have been using up to 10, especially when we do like downscaling of like climate projection, where we only have like the 1 degree nominal resolution CMIP style model to downscale. As you can see, it's usually not possible to satisfy all those conditions, and that's why like regional model is, interestingly, it's a very subjective problem, and you really have to essentially rely on your own intuition of like what is the most important thing that I need to satisfy to get a quality simulation out of my regional domain, because it's not like you can follow like the perfect recipe and you will get the best like regional model. There is always compromise that need to happen. So then you go into like the processes. So what are the main features that you need to get right to be able to answer like the scientific question you are interested in? So again, like do I need like to have tide? Do I need like a BGC model? Does my configuration would require a sea ice model? How much resolution do I need to put to satisfy to get a quality, good quality simulation? One aspect is maybe to consider also is like storage. So depending on the question and the type of feature, like you may need to save like high frequency, for example, temporal output, and so storage will potentially start to be an issue. So then that may constrain your like how big your domain essentially is going to be, because because yeah, if you can run the model but not store the data and analyze them, it's not very useful. So how much resolution do you need? Well, that's not that. I mean, so this is like one example. So it's like that chart was created by Bob Alberg, like I think it was around 2011, and it's just give you a sense of like what resolution you need to be considered like AD resolving. And by AD resolving, we mean that we resolve the baroclinic, the first baroclinic deformation radius with 2 delta x. And so what you can see is that when you move at higher latitude, essentially you need a lot more resolution. And also when you move like more like a coastal region where you have relatively shallow ocean over the continental shelf, you need even higher resolution. And I could have used that chart actually at the beginning to illustrate like why we need regional model, because let me tell you, like it's not going to be anytime soon that we get like a global like 1/50th of a degree MOM6 simulation that we can use globally at climate scale. So there is, I think, still a good space for regional application based on that. So once you have your figure out like what your delta x should be, then the next one is usually like getting an idea of like what time step I need. And so for this, you can use like the CFL condition that can give you like essentially a necessary condition for stability of the model. And it's just like relating essentially the fast moving stuff in the model with delta x, and so you can infer like delta t. So the maximum current number, we typically use like around 0.8. A lot of time when you create a regional model, like you may want to run with like a more conservative time step at the beginning, and then when the model is into its own state after the initial shock, like you can maybe run with a longer time step. But usually, yeah, 0.8 is like we don't want to be higher than that, because even if your model doesn't blow up, like the numeric will not do a great job if you push it too much. There is also some consideration that you can use for like, for example, determine like what horizontal viscosity do you want. So you can use, for example, like the spin down time of like the wavelength, and the smaller wavelength again will be 2 delta x, and you get this like damping time scale based on that, and so that will help you like determine the viscosity using those two ratio. So the idea is like this damping time scale need to be resolved by your model time step, and you want to damp stuff at the grid level. But you don't want to, so you want the time step essentially to be long enough that you will damp stuff at the grid level, but not too long so you don't damp what you are after, like 80s and the dynamic you want to resolve. Alistair touched on that earlier, like another consideration that we used to is like going back to the Monterey. So you have the Western boundary length scale. And so you want your delta x to resolve that boundary length scale. And that the implication was like way back when we tend to have like coarser models, sometimes you had to bump essentially the viscosity so that you will resolve it. I think nowadays we tend to run like with resolution that are fine enough that is not really something that is a concern anymore. But I just wanted to highlight like some of the thing that you can consider essentially to help like design your model and define the parameter set. So know that the next step is like starting to think about like what I'm going to do for the mesh, and usually there is 2 options that are available. One is to use like a global subset of an existing a subset of an existing like global configuration. And So this has some advantages, like you don't have to create the mesh, you will just like extract it from a global grid. You don't have to create like the lensing mask and the topography. So it's like essentially making your job easier. It's also has like potential for like down the road. It's not something that MOM6 can do right now, but I mean, it's always something like when you think about regional, that is something that people will like to do, is like online online nesting, and or even like two-way nesting, where like your regional model essentially can feed back to the global model that you embedded it in. The other option is like just like a standalone grid where you create the mesh and so this one is good because it's like you can really tailor the grid for your application. So it's more flexible than the extracting a global subset. And also you can use like different like map projection. Kate will touch on that more in depth later. But yeah, that's so it's a little bit more work, but you can really get a regional model that is more tailored for your application. So just to illustrate those 2 points, so this is like the mesh that we created for MOM6 at NCAR, and we essentially created a hierarchy. Well, there is like the 2/3 of the degree that is like kind of a standalone grid, because this one uses tropical mesh refinement. So it's hard to do this. It's impossible essentially to do this exercise. But we also created like a hierarchy of like a 1/4 degree, 1/12, and 1/36 grid. So the 1/4 degree is like the larger picture there. And then I have the 1/12 and the 1/36, and you kind of like, if you, it's not how easy, but no, I didn't touch it. So the smaller scale, you have the 1/36, and then you have the 1/12, and the 1/4 degree will be this bigger cell. So all the meshes are co-localized, and so you can go from one to the other away from the coastline by just like doing some block averaging essentially. So that's will really be neat, like for like extracting essentially open boundary condition for your regional domain from the global MOM6 simulation. I think Alper touched on that. Like when we, for like global model, we do have to resolve like the North Pole of the mesh singularity, and so you kind of see like that in the grid with the, so we use a bipolar North Pole hemisphere, and you can see that the density of like cell essentially is pretty high around the 2 pole. And so that's one of the reasons why sometimes can be better to use your own custom grid, because like, for example, if you are interested in building a model on at high latitude, like then you can use like a North Polar stereographic projection, and then you have like a simple rectangular grid that will cover like the North Pole, but doesn't have like a grid singularity that like we have in a global configuration. So now I'm going to talk more specifically about open boundary condition in the model. You saw that chart from Alistair yesterday. So when the open boundary were designed in MOM6, the main idea was to make them as flexible as possible. So typically, like in regional model, in ocean regional model, when we think about open boundary, you really think about the edges of your domain. In MOM6, you have the ability to prescribe the boundary inside, and essentially you can think at the boundary as this OBC as just like a line along which you are going to solve like a different set of equation, your OBC essentially equation, and not something that is like on the edge. The OBC, those segments essentially, or whatever you want to call them, they can overlap. So that's also like hiding flexibility. So you and it's not illustrated in that chart, but like so all the ages know like between 5 and 6 and 6 and 7, they are concave, but like MOM6 also support like convex edges. So it's essentially extremely flexible, and I think it will be very powerful, especially when we if we think about like embedding regional configuration into a global configuration. But even for like standalone configuration, I mean, I build like model where having this kind of capability, this kind of flexibility will have been a game changer. And I was using ROMs at the time, and so we were stuck with having the boundary on the edges. And so I think that's a very neat feature that they created. So you also heard a lot, many times already, that MOM6 is run on an Arakawa C grid. So in terms of like OBC, what does that mean is we need to provide free surface, we need to provide normal velocity at the center, at the face, on the faces, essentially. That's like new from MOM6. You need to also to provide tangential velocity, and this is because of the vector invariant formulation of MOM6. And then you provide tracers, so the minimum is typically like temperature and salinity, but if you have BGC, you will have like a lot more. And I think we also heard a few times already that with MOM6, there is like layer thicknesses, and this is a work in progress. That's why you heard yesterday that MOM6 regional essentially can only be run in Z-star with Z-star vertical coordinate yesterday, and I will add more later on this. So for the barotropic mode, we typically use like flather. So that actually worked pretty well, and it was used in ROMs, and it's worked well in MOM6 too. So you relate essentially the barotropic and sea surface height at the boundary with the same quantity inside your domain. And again, this is like working well. The trouble starts when we start to consider the bioclinic OBC. And so for that, we are typically using like radiation condition. So Orlansky, 1976, it's like normal radiation, and then there was like the oblique was introduced later in 84. So the assumption here is like so you can infer like the phase speed based on the inside quantities. And then the assumption is that those phase speed are actually slowly changing compared to the field you diagnose them from. And so then you can use this equation to extrapolate your inside information at the boundary. And that's worked relatively well when you have a passive boundary. So essentially it let like stuff go out of the model relatively cleanly without reflection. But you're stuck with like under-prescribed issue for like stuff that come inside the model. So when those like phase speed essentially are coming in, what you need, like how do you pass that information inside? And so that's what like Patrick Marchesello and the UCLA ROMs folk like introduce this like nudging ID where essentially you will strongly nudge to the quantity that you get from your open boundary condition when the flow is coming inside, and we still like you apply some nudging when the stuff is going out because it helps stabilize the boundary, but usually there is like a 2 order of magnitude in terms of like the strength of the nudging between the outflow inflow. So typically we use like maybe a few days for inflow and something like a few hundred days for the outflow. So as I say, for MOM6, we also need to prescribe like open boundary for tangential velocity. So there is a few options, free sleep. You can prescribe the dx, dvdx, dy from like the outside if you have a model. can use that. I think most of the time people will end up using like the same radiation nudging condition that I introduced earlier. I mean, another option is always to use zero gradient when you don't know what to do. That's usually what you end up doing. So essentially, you're saying that your condition at the boundary is the same from just inside in the model that you're running. So a little bit more on open boundary condition. So as I say, you need also condition for the tracer. So MOM6 introduced this idea of like reservoir to prescribe this the tracer boundary condition. So the reservoir essentially they account for everything that leave the domain, and then you can mix that with like stuff coming in from the boundary, and the user can specify some time scale essentially at which we will define like the mixing rate between the two, and that's what you use. Layer thickness. So you may have seen some MOM6 regional configuration using non-Z-star vertical grid. Like I know that Enrique did some. And in those configuration, my understanding that he was using zero gradient. So essentially he was saying, well, I don't know what to do with layer thickness, so I'm just going to use what the regional models say they are at the boundary. It's not, we know, I've learned that it's not working in those simulation. The water masses get destroyed like if you run the model long enough. And so there's a need for like something else. And so there is like this new reservoir option that has been implemented, but as far as I know, it's not been tested yet. And the reservoir is not going to be the answer, like the full answer, because the reservoir is just a way to prescribe the boundary, but you still need to feed the reservoir with something at the boundary. And typically when you run, if you run with like a reanalysis, you don't have those H quantity that you need to pass. So there is still an open question like, oh, we are going to use them. I think one potential thing to do will be to run like the MOM6 regrading on the OBC and get the H's and then use them in the reservoir. But that's, again, like something that need to be implemented and tested. So that's why, as I said at the beginning, it's really a work in progress. So more boundary conditions. So if you want to run with tide, you will also need to prescribe tidal amplitude and phase for the barotropic flow and the elevation. And so usually you get this from like something like TPXO. And then you pass that, and MOM6 is going to use that information to compute that and add that to the non-tidal boundary condition that you pass to the model. There is an option to, if you're going to run like really long simulation, more like climate application, there is an option to modulate the tide with the long like 18.6 year nodal cycle. And usually when you run like regional with tide, if you have like a big enough model, you need to add like the tidal potential forcing, so stuff stay like in phase. It's not the case if you have like a small domain. Usually just prescribing the tide at the boundary is sufficient to get it right. So if you have like just a small bay or something, but if you run like a larger regional domain, you probably want to have like the tidal potential, and that's an option that is already available in MOM6. Last is some detail about the OBC file in MOM6. So the model will read essentially the OBC from file, and it will read the quantity, but also the vertical grid from the file. So you have like many file like salt segment 1, and that will include like DZ segment 1, so that the vertical information. Each segment each segment and each field. So yeah, each file essentially provide like the information about the given tracer or velocity and the vertical structure. And that slide is coming from Kate, sorry. Model does remapping into MOM6. Yeah, so MOM6 is actually, that's like a neat feature. I forgot about that. Like when you work with ROMs, you need to do the vertical interpolation. So you provide your OBC directly on the vertical grid that ROMs is using, which is a lot of work. You don't have to do that with MOM6. You just prescribe the boundary on whatever grid you're in, and then like MOM6 will do the job internally for you and remap. So that's pretty nice. And yeah, again, like it's unclear what ought to provide essentially the information for the thickness at the boundary to be used with those reservoir conditions that have been implemented. So so yeah, that's something that need more work and is ongoing. So I'm going to pass it to Kate now, and she's going to walk through more like in-depth grid generation, map projection, and also some concrete example of like creating regional configuration. Sure.
Why is it needed? Like, let's keep it simple for tracers. Like, why can't you just like, you know what the, I mean.
Well, you can, I don't know if,
So in the ROM space, what we would do is we would have image points of all from the open boundaries. And in the image point values, we're keeping track of the relative flow of what's going out and what's coming in. And this is a way to not need an image point. So you have a reservoir right on the boundary.
They got it. Yeah.
Yeah, you cannot direct. I mean, one option with the boundary is just clamp. So you prescribe what is coming out, but this is usually incompatible with like what the regional model think the condition is just inside. And so if you just like prescribe the condition, like it's going to create a lot of issue around your open boundary. So the reservoir is a way to do that a little bit smoother. Same way, like same thing with the baroclinic condition. That's why we use nudging, and we just don't prescribe directly what the quality coming in is, because then it will create like instability and a lot of issue reflection and etc. So we need to prescribe something, but you don't want to be too aggressive essentially, and the nudging is a way to do that. And the same thing, like the reservoir is a way to prescribe stuff without oversubscribing essentially the problem.
Yeah, thanks.
Thanks, Fred. So I'm bringing my favorite tool for designing regional domains. And it allows you to look at, where do you want your domain to be and what angle do you want it to be at and so on. And so this is spherical-ish, and the tools I use for creating grids all work on a flat plane. And so you need a way to go from the sphere to the flat plane, and that's where the map projections come in. And the three most commonly used map projections that I know of are stereographic, which is usually a polar stereographic for either the North Pole or the South Pole. Although in general, a stereographic projection is just a tangent at a point. The next class is Mercator, often used for near equatorial domains. And it's touching the sphere in a circle. And usually that's oriented so that where it touches is at the equator. And then the math is easier with that. And the third kind of projection is Lambert conformal conic, where you have one or two lines of latitude where the sphere and the cone touch. And that's often used for mid-latitude kind of domains. So the way to do this is you find your domain boundary using the coastlines from the latitude longitude coastline file or whatever means you use. And then you need a conformal map projection to obtain the boundary X and Y. And then you create a grid in that XY Euclidean space. And then you need an inverse map projection to go back onto the sphere where you recompute the grid metrics, because the grid metrics are what MOM6 is using in the internal to the calculations. Any of the horizontal gradient terms have a grid metric in them. Here's an example of a curvilinear orthogonal grid. And you start by drawing the boundary, the outer boundary of the grid. And then the interior gets filled in by your gridding method. And you can control the grid spacing on two adjacent edges with this particular code. And so in this case, the outer edge has uniform grid spacing. And then what you get at the inner edge, the coastal edge, is what you get. I mean, that's just what happens. And then you also, the southern boundary has finer resolution toward the coast, but gently and slowly and gradually. You don't want any jumps in the resolution. It's best to give it 4 90-degree corners, and there's fine resolution at capes and coarse resolution at bays. Is what happens as you're bringing the grids from your uniform spacing out here toward the coast. And zooming in, you can see it more here. And so the algorithm this program uses has complex math in it. And that's why you need a flat geometry. And we do need masking because I'm not following the coastline as carefully as the real coastline. There's bumps I'm not resolving. And also there's islands. So this is Santa Barbara Channel area. And the time step is limited by the finest spacing of the water points. And to give an idea of how badly the staircase coastline is doing for us, Dale Hadevogel came up with a test problem. So there's an analytic solution in a circular domain on an F-plane. And we had 3 waves around the edge, and the waves just propagate unchanged around. And what we're doing here is looking here. Oh, anyway, these 5 curves are from 5 different resolutions of the circle problem. And the coarsest has the biggest phase error. So the correlation should be 1 at a 0 angle if it had moved as far as it should have, but it's been slowed down by hitting all these little staircases in the coastline. And also shown below that are these curves. And this is the sea surface height all around the edge of the domain. And you can see that this red one especially is just really noisy. So the solution is getting noisy from hitting all these little staircases. And a different way to mesh this problem is shown on the circle, this one. And this is an annulus, so I don't have the pole problem exactly. And these curves down here, man, no wonder he's not using it. Show that our solutions have much less phase error in the annular domain, and it's better when the resolution at the outer edge is finer. So the difference between the 2 curves is the one on the right has finer resolution around the circle so that the cells at the edge of the domain are square rather than these big rectangles. So what I showed you with the California domain was using one algorithm for producing a curvilinear orthogonal mesh. This is a different algorithm written by Pavel Sakov. And you can provide not just the 4 90-degree corners, but more 90-degree corners, as long as you also include minus 90-degree corners to balance them out. So here, these 2 extra corners are balanced by these 2 extra corners. And this is a crazy domain, and I don't think it makes sense oceanographically, but it's around Indonesia with Java to the south. But the point is that MOM6 would be perfectly happy running on this domain. And this the green open boundary can be a completely different segment from the purple open boundary over there at the top, at the northern. What? Oh. Anyway, so you can have completely different physics. You can have one be an outflow domain or segment and one be an inflow segment. And this whole thing with Borneo in the middle, that can just be masked out in your mask table and you don't have to worry about it. Okay, once you have a mesh, the next step is putting a bathymetry on it. And again, this is an old slide. And so back in the day, eTopo 5 was on 5-minute resolution, and it was really quite smooth. So this is a domain where I don't have a Hudson Canyon. Here's the Hudson River outflow, and the canyon is kind of washed out. And an alternate choice is Smith and Sandwell, which does have a Hudson Canyon, but it also has these unphysical bumps or pits in the coastal ocean, and it's just really unsatisfactory. And now everybody's using Gebco for better or worse, and hopefully it doesn't have quite as many obvious pits like that, and it's really high resolution. And it's so high resolution that you don't want to just use a simple bilinear interpolation. And Alistair came up with a method to take all the bathymetric points in your grid cell and figure out a way to come up with an estimate of what the depth is there and also the bottom roughness. And he didn't mention an internal tidal parameterization, but MOM6 does have one that needs a bottom roughness estimate. And there's also a sea ice parameterization that needs a bottom roughness estimate. No, you don't have to smooth it. It's so wonderful. Yeah. If you use, well, we don't have that many tests using the bathymetry column coordinate. It is supported, the sigma coordinate is supported in MOM6, but I've used it in a few test problems, but nothing realistic. The typical workflow, we went through this yesterday with the crocodile. You start with figuring out where your domain boundaries are going to be. You generate your grid, your bathymetry, your landmass. And they talked about how to turn off the domains that aren't connected in your domain, like the water parts of your domain. If you have multiple bodies of water, you need to simplify it to just have one. But one thing you need to know is that the radiation boundary conditions require 3 water cells adjacent to each open edge. So this circled black circle here is pointing out an area where I've got less than 3 water cells next to the open boundary. And I need to fix that before I can go on and run things if I want to use a radiation boundary condition. And so that you edit the landmass before going on to the next steps. which is to generate the OBC file and the tidal OBC file and the rivers file, because the river remapping needs to know where the coastline is in the final version of your landmass. And then you go on to the biogeochemistry files if you need those for the open boundaries. And atmospheric fields are just coming in as the global file. We don't have to do any remapping or anything. The model does that for us. So that's kind of nice. So getting into the nitty gritty, I was playing with Crocodile a couple months back. And this is the Resurrection Bay in the Gulf of Alaska, and 2 different attempts at making a mesh there. And so just thinking about which one of these domains is better and why. And so to talk about the Gulf of Alaska more generally, you've got, there's a North Pacific current, and it splits, some goes south, some goes north. And this is more or less following the shelf break out here, which is pretty far offshore along, here's Kodiak Island. And the Resurrection Bay is where these red marks are, more or less. So that it's not going to see the Alaskan stream at all, but the domain will see this brown current, which is the Alaska coastal current. And this is driven by freshwater runoff from, there's some precipitation gauges, and the scale here is 2 meters per year of precipitation. Some of these go up to around 8 meters a year on average. And these are not at gauged rivers. These are just water that's falling on these fjords and then running right into the ocean. And what it does is it produces a strong coastal current based on the freshwater density gradient, right? Following the coast very closely. So in the domain we showed before, I like the domain on the right better because you'll have that coastal current coming in on the eastern boundary and leaving on the southern boundary. And what's going on in the other domain is more complicated. So you'd have it coming in on the eastern domain, and then on the western domain, it's coming in and out, and then going out the south. Just a note that I'll be showing a Glacier Bay grid later, and Glacier Bay is here. Workflow continued. So you take your Crocodile files, or you can take files that is running and edit it what it needs to have changed to be suitable for your new domain. Let's start from the Crocodile files because it's already giving you the MOM input and all of that. And you have to try running it. And then when it blows up, you have to fix it. And then, so common mistakes to look for are problems in your input files. So really examine your input files. That domain I showed on the left for the Resurrection Bay, the western boundary coming from Glorious, didn't have valid values along that whole western open boundary, so that was not going to work. So that's a problem where the landmass didn't match from the parent grid to the child grid. You also have to do some trial and error to find a time step or set of time steps you're happy with. But there are other random weird things that can happen, like the river remapping from GLOFAS. I had a case where the Mackenzie River outflow in GLOFAS ends not at the coast, but inland a bit. And you need to account for that when you're doing the remapping. You have to give it some distance to carry those outflow cells to the coastline of your domain. So once it runs for a year or more, that's when things get harder, I think. And that's when you need to come up with some metrics to find out how well you're doing. And common things people look at are temperature and salinity and how you compare to World Ocean Atlas. Or for the BGC, how you compare to the nutrient fields. And you need to check to make sure your tides are realistic. Also, people look at energetics. Do they match the energetics that come from the satellite estimates of where the eddies are? And if you have sea ice, what's the extent, sea ice extent and the timing and so forth? Does that all make sense? So some examples. We have a Nicole has a southwest Atlantic domain. And the goal of this domain is to study the confluence of the Malvinas and Brazil currents. And she needed a domain large enough not to have the open boundaries too close to that confluence region. And she did a good job of reproducing the Southwest Atlantic, but there are still some problems, as always. And so here's her domain. It goes from 5 north to 55 south, and it has a good range of longitude. For instance, that California grid I showed early on, that does not have a wide enough range of longitude. So the California eddies would kind of bump up against that boundary. So it's not a good example of how to build a grid. This is a better example, having a wider offshore extent. So on the right here, we have observation or comparisons to observations for at the top sea surface temperature. In the middle is sea surface salinity, and the bottom is mixed layer depth. And everything looks really, really good. These are 20-year means, so you're smoothing out a lot, but the remaining problems are freshwater at the mouth of the Amazon River and the La Plata River. And it wasn't a deal breaker on her getting a PhD, so all is good. Second example is an Arctic domain. And it's a multi-person effort with biogeochemistry. And this is driven by the CEPHI project you might hear about tomorrow, should hear about tomorrow. It includes sea ice. And since we don't have ice open boundary conditions, we put the boundaries far enough away that it's not really a concern. And Fred showed that the grid we're using at a coarser resolution, but yeah, that's the domain we're using. So it's a polar stereographic projection. And if I were to do it again, I would pick a subset of a tripolar grid, just the way the grid, yeah, anyway. And the coupled ice ocean model doesn't support wetting and drying at this time. And so I needed a 5-meter minimum depth for stability. Otherwise, the dry cells would cause the whole model to blow up. Arctic challenges, various temperature and salinity drifts, sensitivity to sea surface salinity nudging, excessive vertical mixing on the Atlantic side. And Teresa Cordero has taken over the running of this domain, and she has added a nudging to climatology around the edges. So that's another input field you might have to generate at some point, is what we call sponging in MOM6 world. So it's just a climatology of the whole 3D domain at, say, monthly time resolution. And you do nudging toward that. And that can help control the temperature salinity biases, which cause trouble for the biogeochemistry anytime you have physical biases. And again, you should hear about this domain tomorrow. My last example is a Glacier Bay domain. So Seth Danielson talked his daughter Helen into investigating nutrient fluxes into Glacier Bay as a high school senior project. And it's a mostly enclosed bay that has very high productivity, which is why it's a national park, because it's got lots of marine mammals and birds and so on, and more than the nearby fjords. So the question is, can the glacier melt and the runoff provide the nutrients needed to support all this productivity? And if not, can those nutrients be coming in from the Pacific Ocean? And they asked me for a 0.5 kilometer resolution, so that's what they got. Although this is not obeying that 3-to-1 kind of ratio Fred was talking about. This is a 20-to-1 ratio. So here's the domain. It's, oh, I see. North is kind of off at an angle. See if I can. North is kind of this way. And the Pacific Ocean is off to the west. And the rest of the Alexander Archipelago is down to the south, in the southeast. And let's see. This is a movie. So this is the start of the movie, which is the run started on January 1st. And what we're looking at here are two different dyes, dye 1 and dye 2. Just ignore dye 3. I don't know. Yeah. Anyway, so dye 1 on January 1st was initialized with a value of 1 everywhere below 20 meters depth. And dye 2 was initialized with 0 everywhere. But anytime water flows past, this narrows here, it gets painted with that dye 2 with a value of 1. So does the movie play? Is the question. What? Oh. Oh. It's, anyway, asking for access, but it's Seth Danielson's movie, so anyway, so what happens in the movie is it runs from July to the end of the year, and it starts off with dye 1, you know, is filling this whole basin here. So it's got a really deep basin. We're looking at the, anyway, what happens is dye 1 stays in the deep basin for part of the year. And then as you get into the fall, when it becomes less stratified, some of that dye 2 gets into the deep basin. And by the end of the year, you have the whole basin is filled with dye 2 and none of dye 1. And I have to make this thing go away, and I don't know how to do that. Oh, go to next. No. It's what? Well, the focus is on a screen that's asking for permission to show the movie. I don't know how to make it go away. Oh, there. Okay. So in conclusion, learn about your domain first. And I built my career on solving the easy problems, like fixing the perfect restart kinds of things that go bad quickly. And harder problems are still there, coming up with metrics and how to improve model performance. And you're here in a group setting, so you know you're not alone. There are regional Mom6 biweekly meetings, and Andrew Ross is running these. You can ask. I guess he would have been presenting here, but due to the shutdown, he's not. Anyway, he will eventually be able to answer your emails, and he could add you to these. And there's also an NCAR hosted forum about Mom6 at this URL. And the goal is to have kind of a history of Q&A about common Mom6 regional problems, or not necessarily regional, but Mom6 problems. So And thank you.
Right, time for questions, yep.
So in ROMs, we have, in a OBC, we can assign the U bar and V bar at the boundaries. In MOM 4, there was a few test cases which were providing this facility of UD and VD as the OBC. MOM 5, I've never seen any case which assigns depth average currents in the OBC. So does MOM 6 provide that facility? Because when I was creating a domain in Gulf of Mexico, and if I was not giving U bar properly, then my loop current was completely disturbed.
I believe it keeps itself from the boundary U values.
But we don't have provision to externally provide.
I don't think so, no.
When we're specifying open boundary conditions for like velocity or like volume transport, does MOM 6 automatically like satisfy continuity? Or do you have to go in and make sure that like you're not creating or destroying mass?
Well, you're not gonna be conserving things if you have flux through the boundary. Flaler does a really good job of keeping the sea surface kind of uniformish. So you're not gonna just drain all your fluid out over time.
Is that like a audit? Do we have to do that ourselves or is that part of like the MOM 6 package?
It happens with the way the flaler is implemented.
Oh, okay, thank you.
I saw MOM6 also support tidal potential if we use a very large domain. So, but from yesterday's talk, we know the three-dimensional equation also has potential term. So in Ross model, the tidal motion is mainly served by the shallow water equation. So my question is whether the tidal potential also added into the potential term in the three-dimensional equation.
In MOM 6 or ROMs?
MOM6. I know ROMs does not.
It's in there. It's been in there since gold, so.
So MOM6 only add tidal potential into the shallow water equation, you mean, right?
Yeah, I think so.
Okay.
So one more question. I will selfishly ask a question. Actually, I do too. So Alistair, you mentioned this morning that the biharmonic viscosity was a good option for higher resolution. And I was wondering if you could maybe qualify what you meant by that. And then I guess more broadly, are there templates of some of these choices that might be appropriate for, regional models at the 1 kilometer or the 10 kilometer kind of scale? I guess maybe that's a question for you and Fred.
Well, I think Fred said it. I mean, basically, you do need to consider how much dissipation you're going to put in. I think my point was that if you are in a inertial regime where you're resolving eddying motions, which you generally are going to be in regional models, the passing will be too smoothing. It's not scale selective enough. I don't know what the highest order of operator you had in ROMs is, but I mean, the highest we have right now is biharmonic. I know that in MIT, there's actually higher order filters, and that's something we can consider adding. You can go to even higher order to make it even more scale selective. But at the time being, we have biharmonic, and the biharmonic, you just need to have enough that it's going to control the noise, and then let the model handle the rest. So, I mean, I would be surprised if it's something you change very often. I mean, if you could with Melon's number, say 5 or 10, you're good to go. Only ones we always use biharmonic. I don't know anybody that we use that.
In ROMs, we had a constant value for the biharmonic. And using the Snagorinsky, so it's got the tensor.
Okay. Well, thanks to Fred and Kate. We can now break for lunch and let's thank them one more time.